So just to catch up, I just wanted to make a short video going through Liouville's theorem, which is essentially a statement about phase space volume and that is going to be preserved. So Liouville's theorem, that's a theorem which says that phase space volume is preserved under these flows generated by the functions we just discussed. So a flow preserves a volume if the divergence of the flow tangent is 0. So essentially that means that as much is flowing in as is flowing out of any given volume. In that case, we're going to have preservation of the phase space volume. So what does this mean in phase space? Well, phase space is 2n dimensional. So in 2n dimensional phase space, what you want is the divergence of dr of the flow tangent to be equal to 0. So what this means, if I just write it out in terms of q's and p's, this means that d dot qa plus d p dot b dpb, this should be equal to 0, right? If this is the case, then my phase space volume is preserved. So let's now assume that I have a flow that is generated by some function g. So the tangent vector components, they're just given by this Poisson commutator with g. Okay? In that case, what does that mean? Well, it means that if I take this derivative, I can replace y dot r by this Poisson commutator. So I get the r yr g. But now, assuming that that derivatives commute and so on, I can just use the product rule here for the derivatives. I get two terms. I get dr yr with the commutator with g, plus I get another term where I have the yr and I act with the derivative on the function g itself. Right? Now, this first term here, dr yr, that's a delta function summed over the diagonal essentially. So this entire thing is 2n, where n is the dimension of configuration space, so 2n is the dimension of phase space. So then you have a constant commuting, the Poisson commutator of a constant and the function g, that's always 0, because whenever you differentiate the constant, you get 0. So we are left with only this term. So what we obtain from this commutator is dyr, dyt, then the commutator yt, ys, and then ds acting on drg. Okay, and so we can look here at this derivative. This is a delta rt. This thing here is by definition omega ts. So what we are left with in the end here is omega rs ds drg. But now we know that this omega, which is by definition the Poisson commutator of yt, of yr and ys here, that's antisymmetric when I exchange r and s, whereas assuming that these derivatives commute, ds and dr, this expression here is symmetric in S and R. So that means that everything is 0, meaning that the phase space volume indeed is preserved. And this is then known as Liouville's theorem, which can come in handy at many times.